Okay, good afternoon, everyone. It is 12:30. I do want to go ahead and kick things off since this is just a 30-minute session. So welcome to the SAS Viya Transition Lunch and Learn session. There's two links here to visit some upcoming resources and to learn more about office hours and other offerings and the topics that are going to be coming up there. Laura will go ahead and drop those in the chat soon. So just a couple administrative announcements to keep in mind as we kick things off. This meeting is being recorded. Please stay muted to minimize interruptions while Eddie is presenting. And then this session will not feature a Q&A session, but instead we're going to ask that there's going to be a Zoom survey at the end of our session. And the very last question is going to refer to a Q&A session that we're going to be hosting soon. And we're looking for topics and looking for questions that we want to address during that Q&A session. So we're going to ask that if you have a question, because this is such a short session, that you go ahead and add it there so we can address it. And then all meeting materials are going to be made available in the CCSQ DNA portal. So with that, I'm going to go ahead and stop sharing and pass things over to Eddie now to give you more information about today's session.
Okay, thanks, Julia. I think I just sent you the request. All right, great. Can you guys see like a Databricks notebook?
Yep, now we can. Looks good.
All right, great. And then if I go like this, you see kind of a drawing behind it. Do you guys see like another screen there, like a drawing?
No, I don't think so. Laura, do you?
I do not, but I see like a gray box at the very top of your screen.
Okay. Sorry, just make sure if I switch, this is so you guys don't see like a drawing or anything right there.
We see the diagram right now.
Oh, okay, cool. Sorry. Okay. Sorry about that. All right, cool. So yeah, thanks again. My name is Eddie Chia. I joined the user services team as a staff data scientist about a month and a half ago. I have almost 15 years of experience in analytics. I have an undergraduate degree in statistics and a graduate degree in machine learning and artificial intelligence. I started off my career really as a statistician and a SAS programmer. But in the fall of 2017, I joined a company named 8451. They are Kroger's analytics arm. And with all of the other data scientists and engineers, we made the transition from SAS to Databricks. So over those, I'd say 3.5 years, I was able to use a lot of different tools and platforms from SAS to Hadoop to different cloud service providers like Microsoft Azure and Amazon Web Services. And so my goal really with this Lunch and Learn is to kind of give a high level overview of some of those platforms and tools and show how they are connected. All right, so let me just switch to here. Okay. All right. So how did the internet really change the data that's being created and collected? So traditionally, a lot of the data that was being collected came in column row format. So think of a table in a database or a CSV, with the schema. But with the internet and a lot of this new data, we started seeing more text, more images, video, and even audio files. So to understand our data, traditionally we would apply the 3 V's of volume, variety, and velocity. But with all of this new data, the community added variability and veracity. So volume, the quantity of data generated and stored. Like I had mentioned, the amount of data that we're collecting, over the last 20 years or so has just kind of grown exponentially. The variety, so the type and nature of data. So again, we're moving from columns and rows with your typical data types of string and integer to now, images and video and audio files. Velocity, the speed of data generation and processing. So I'll get into this in a little bit, but traditionally we would, use batch processing. So maybe you run a script once a day. At that point, it would collect all the data, it would analyze it, and then give you the results. You'd have to wait to the following batch to get the next results. But now with social media, really there's a focus on real-time processing. Variability, so the inconsistency of the data set. So now the same value can have like a different meaning. So think of the word book. I read a book. I booked my flight. Depending on the context, it could have a different meaning. And finally, veracity. So the quality and certainty of the data captured. So now we're collecting all this data. How much of that data is actually accurate, and how much of it is error. All right, so now that we have kind of an understanding of that kind of new big data, what do we do with it? All right, we're going to have to process it. We're going to have to analyze it. So, in terms of the processing, we actually have to redefine what processing means. So now it's, we have to process large and complex data sets that traditional database systems are unable to handle. And again, traditionally we would use batch processing, but really a lot of focus needs to be on that real-time processing. And then in terms of the analytics, so a set of techniques and technologies used to extract insights from diverse, complex, and large data sets. So, we still have your traditional statistics, with your kind of column and rows data, but with more and more structured or semi-structured data, we started getting into machine learning. I just want to make a call out to the unsupervised learning section and really like the cluster analysis and the dimensionality reduction. But really, it's this kind of new branch of analytics with artificial intelligence where we're seeing, a lot of the rapid growth in research and application. So we're looking here at the advanced natural language processing, computer vision, and recommender systems. All right, so now that we kind of have an idea of like the type of processing that we need and the type of analytics that we can do, what are some of the big data platform requirements? So one, we're going to need to store high volumes of data arriving at a higher velocity. Two, accommodate structured, semi-structured, and unstructured data variety. Three, process high volumes of a variety of data at a higher velocity. So in order to kind of meet those requirements, there are two approaches. We have your historical kind of approach, traditional approach with monolithic. So think of your relational databases with tables and a schema. There's also been research and application done in NoSQL databases, where now they're starting to process semi-structured and unstructured data, even in real time. However, it's going to always run into a scalability issue, which is why most of the research and application has been on distributed processing. So Google, in the early 2000s, they were facing the same data needs and the same data requirements. They summarized those three requirements with the following four objectives. So data collection and ingestion, data storage and management, data processing and transformation, and data access and retrieval. So their solutions to these four different objectives were published in two really major papers, the Google File System in 2003 and the MapReduce in 2004. So in order to kind of explain what those are, I'm going to kind of use an example. So I want you guys to think of a newspaper that has sections. So think of like the Washington Post or the New York Times, right? There's a sports section, there's a science section, art section. Let's say that there are 10 sections. It takes me 1 hour to read, process, and summarize each section. If there are 10 sections, that means I would summarize the entire newspaper in about 10 hours. So that's your kind of monolithic approach. Now, your distributed approach, I can ask, 10 friends, or really I can clone myself 10 times. I can give each person, a section of the newspaper. I can ask them to read it, process it, and analyze it. I, note who I gave each section to and how they are kind of processing it. And I also make note that once they give me all the sections back together, I can put it all back into that one kind of unified newspaper that you see. And so that's kind of your distributed approach. Your Google file system really is how the newspaper is divided into kind of 10 sections, and the MapReduce is how those sections are, analyzed and processed, and how it's then kind of aggregated up to that newspaper level. All right, so now that we have, the distributed storage and distributed computing with MapReduce, what is Hadoop, and how does it fit in? So Hadoop is an open source framework designed for processing and storing large scale data across distributed computing environments. It consists of several key components, and really the first two came from those two published papers by Google. All right, so you have your HDFS, or your Hadoop distributed file system, instead of GFS. HDFS is the storage layer in Hadoop, designed to store vast amounts of data across multiple machines. It splits files into blocks, which are replicated for fault tolerance, enabling data to be stored and accessed efficiently across clusters. And then two, you have MapReduce, or your distributed computing. MapReduce is a programming model for processing large data sets in parallel. The model consists of two phases. The map phase, where data is processed in parallel across the cluster, and the reduce phase, where results are aggregated. And finally, the third component, or Yarn, or yet another resource negotiator. Yarn manages the cluster resources and schedules tasks across the cluster. It enables resource allocation for different applications, such as MapReduce, ensuring efficient use of computational resources. So, despite its strengths, Hadoop has its limitations. It relies on disk-based storage and processing, which can be slow, particularly for iterative tasks. The programming model is also complex and requires expertise in MapReduce, making development challenging. So if we just looked at the data access piece within the ecosystem, we can see that it would take a lot of tools and resources to complete an entire data pipeline from beginning to end. And additionally, Hadoop's real-time processing capabilities are limited, requiring tools like Apache Spark for faster, more flexible processing. All right, so what is Apache Spark, and how is it an improvement over Hadoop, and specifically MapReduce, or distributed computing? Apache Spark is an open source distributed computing engine for fast, scalable big data processing. It supports both batch and real-time analytics. One of the central features to Apache Spark is the resilient distributed data set, or RDD. RDDs are the fundamental data structure in Apache Spark, representing distributed collections of objects. They are immutable, fault tolerant, and enable parallel processing, which allows for efficient and scalable data processing across multiple nodes in a cluster. The next central piece to Apache Spark really is the data frame, or kind of the version 2 of the RDD. Data frames in Apache Spark are distributed collections of data organized into named columns, enabling efficient querying processing, and transformation of structured data in a distributed environment. Data frames are more efficient than RDBs due to optimized execution, built-in query optimization, and easier integration with SQL, machine learning, and structured data processing. Okay, so let's focus a little bit on the Spark ecosystem. All right. So the Spark ecosystem is a collection of tools and libraries built around Apache Spark to facilitate diverse big data processing tasks. At the center of this ecosystem is the Apache Spark engine, which provides distributed computing capabilities. This enables the efficient processing of massive data sets across a cluster of machines. Here are the key components of Spark ecosystem. First, you have Spark SQL, which this allows users to query structured data using SQL syntax. It supports reading from various data sources like Parquet, JSON, and Hive. It can also integrate with relational databases and data warehouses. Two, Spark Streaming. So this extension of Spark enables real-time data processing. It allows for continuous processing of streams of data, such as logs, sensor data, financial transactions, making it suitable for applications requiring low latency, real-time analytics. Three, MLlib. So this is Spark's machine learning library that offers scalable algorithms for classification, regression, clustering, and recommendations. MLlib simplifies the process of applying machine learning models to large data sets and integrates with Spark's other components for end-to-end data processing. GraphX. So GraphX in Apache Spark is a library for graph processing and analysis, allowing distributed computation on graph structured data. So examples of graph structured data include social networks, web page links, recommendation systems, transportation networks, and biological networks. And finally, Spark R. Spark R is an R package for Apache Spark, providing an interface to Spark's distributed data processing capabilities. It allows our users to perform scalable data analysis and machine learning using Spark's data frames and MLlib. So what are some of the advantages of Spark over Hadoop? First, performance. Spark outperforms Hadoop by processing data in memory, reducing disk I/O, and enabling faster computation for both batch and real-time workloads, while Hadoop relies on slower disk-based MapReduce for batch processing. Two, ease of development. Spark SQL simplifies development by allowing SQL queries on structured data, offering high-level abstractions like data frames. It integrates easily with Hive and other data sources, making it more user-friendly than Hadoop's complex MapReduce approach. Next, language support. So Spark supports multiple programming languages, including Python, Scala, Java, and R, offering flexibility for developers with different expertise. This makes it more accessible than Hadoop, which primarily supports Java. Spark's diverse language support enables faster development and easier integration while existing tools and workflows. Next is storage. So Spark can integrate with various storage systems like HDFS, S3, and NoSQL databases, offering again flexibility. Unlike Hadoop, Spark processes data in memory, reducing reliance on disk storage and improving performance for both batch and real-time tasks. And finally, resource management. So Spark provides better resource management with built-in support for Yarn, Mesos, and Kubernetes, again, enabling flexible, efficient resource allocation across clusters. Hadoop's resource management is primarily reliant on MapReduce, which lacks Spark's scalability and optimization features. All right, so and finally, I think we're getting to the end of the drawing, but so now that we have learned about Spark, what is Databricks and how does it improve Spark? So Databricks is a unified analytics platform built on Apache Spark, offering collaborative tools for data engineering, machine learning, and data science. It provides a managed environment for running Spark, optimized performance, automated cluster management, and integrates seamlessly with cloud storage and various data processing frameworks. Apache Spark, while it's really powerful, it does have several limitations when you compare it to Databricks. So first, the cluster management. Spark requires manual configuration and management of clusters, which can be complex, especially in large environments. Databricks provides an automated, scalable platform with simplified cluster management, auto-scaling, and optimized performance, making it easier for users to set up and manage your Spark clusters. Two, performance optimization. Spark's performance tuning often requires significant manual effort, as users need to adjust configurations for optimal resource usage. Databricks includes performance enhancements such as the Databricks runtime, which provides optimizations, caching, and faster processing, reducing the need for manual tuning. Next, user experience. So Databricks offers a collaborative, user-friendly interface with notebooks, integrated machine learning libraries, and advanced visualization tools, improving productivity for data scientists and analysts. Spark on its own has a steeper learning curve and lacks such built-in features for ease of use. And finally, the integrated ecosystem. Databricks comes with native integrations to various data sources, machine learning, and graph processing tools, making it a more comprehensive platform compared to Spark's standalone version, which may require additional configuration and integration efforts. So overall, Databricks offers a more efficient, simplified, and user-friendly experience when you compare it to Apache Spark. All right, so that is the drawing, and I'm just going to kind of tie it up with a quick recap, right? So let me actually get the full drawing. All right, so let's see, the internet's rapid growth led to the generation, of vast amounts of data from websites, social media, e-commerce, IoT devices, and a lot more. This explosion of data, referred to as big data, overwhelmed, our traditional data processing tools. As a result, new technologies like Hadoop, Spark, and Databricks were developed to manage, process, and analyze this massive volume of data. Hadoop provided a distributed storage with HDFS and processing framework with MapReduce that allowed data to be split across many machines for parallel processing, which really addressed some of the scalability challenges up to that date. Apache Spark enhanced Hadoop's capabilities with in-memory processing, dramatically improving speed and performance for batch and real-time data processing. And finally, Databricks built on Spark, so providing a managed platform that simplified the development and implementation of big data and machine learning workflows, offering collaborative tools and optimized performance. So these technologies enabled businesses to extract value from big data for insights and decision making. So I know we just covered a lot of information. I was trying to provide a high level of I say some of the buzzwords that I learned over a few years as I made this transition. And we'll share the drawing, but I'm hoping that it's kind of maybe added connections or filled in some of the connections between some of these platforms and tools. Are there any questions?
I don't see any questions right now in the chat. Okay, one just, oh, no, that was just Dan Anderson giving some clarification.
Okay.
If you want at this point, though, we can go ahead and go to the survey.
Sure.
Okay, all right, well, thank you so much, Eddie. So I'm gonna go ahead and launch that survey now. Just a reminder, please make sure that you are, if you do have a question that you would like to have answered at a Q&A session, please list that at the end. Okay, so that should be on your screen now. Thank you so much for joining. Once you're done and you've submitted, you can feel free to drop, and we look forward to seeing you at some of our other sessions. Thank you.